Hi everyone, welcome to our discussion in mathematics in the modern world. In this video, I will be discussing our topic in Module 3, which is about sequence. So to start with, let me first define what a sequence is. So a sequence refers to an ordered list of numbers called terms. So take note, these are not just merely numbers, but this is an ordered list of numbers, meaning there is a certain order to these numbers that may have repeated values. So another thing is that the values may or may not be repeated depending on the order of the list. The arrangement of these terms is set by a definite rule. So for it to be called a sequence, there should be a rule, or we simply call that a pattern. So we should observe a certain pattern in those set of numbers. Consider the example below. We have the set of numbers 1, 3, 5, 7, and so on. The first number in our sequence that is called the first term, the second number is called the second term, the third number is the third term, the fourth number is the fourth term, and so on. So as shown above, let me just write that down again. 1, 3, 5, 7, and so on. The elements in the sequence are called terms. Again, each one of these numbers are called terms. Okay? Let me just write that down one more time. 1, 3, 5, 7, and so on. It is called a sequence because because the list is observed, is ordered, I mean, and it follows a certain kind of pattern. I'm sorry for that. Let's proceed. The pattern must be recognized in order to see the expanse. So let's say, for example, we have 1, 3, 5, 7, 9, 11, 13, 15, and so on. And below, we have 1, 3, 5, 7, 8, 9, 10, 20, 22, and so on. If we will be observing set A, or the first set of numbers, so we can say, or we can observe that there is a pattern. So what do you think is that pattern? It's actually adding 2 or 2 to the first number or the first term in order to get the next or the succeeding term. So from 1, add 2, that's 3. Add 2, that's 5, plus 2, that's 7, plus 2, that's 9, plus 2, that's 11, plus 2, that's 13, plus 2, that's 15, and so on. Whereas for the second set of numbers, for set B, the pattern holds only for the first 4 terms. When we arrived at the 5th term, the pattern has changed. It became, or it turned to adding 1 instead of 2. And in the succeeding terms, the pattern changed, or to get the next number, it turned to adding 10, and here we added 2. So therefore, that cannot be called a pattern anymore because it doesn't hold true for all set of numbers. So whatever the pattern is or the rule is, it should hold true for all numbers in our sequence. So therefore, the first set can be considered a sequence. The second set is not a sequence. The three dots at the end of the visible patterns means that the sequence is infinite. So let me just erase that. So that's 15 and so on. So these three dots after our last term here, it means our sequence is infinite, meaning that sequence will still continue. So it's never ending. So we keep on adding 2 in order to get the next terms in the sequence. But let's say, for example, that we do not see the three dots after the last term, we call that sequence as a finite sequence. Finite sequences are sequences that ends. There is a certain ending. There is a last term to it. But if we say infinite, the sequence is never ending. It will never end. It will continue until the next set of numbers. So, by the way, the three dots after the last term that can be seen here, that is read as and so on. Okay, so 1357 and so on. But if ever we or you do not see the three dots, just read it as it is, 1357. So there are different types of sequences or sequence, and most common are what we call as the arithmetic sequence, the geometric sequence, the harmonic sequence, and the Fibonacci sequence. And I think you are familiar or you have heard these terms before because these topics or these concepts were discussed, if not during your senior high school years in grade 11 or 12, most probably when you were in grade 10. So let's proceed with arithmetic sequence. So arithmetic sequence is a sequence of numbers that follow a definite pattern, of course, because it's a sequence, it should have a pattern. To determine if the series of numbers follow an arithmetic sequence, so to identify if the given set of numbers is an arithmetic sequence, check the difference between the two consecutive terms. If the common difference is observed, meaning if the common difference is the same or it holds true for all the set of numbers in our sequence, then definitely arithmetic sequence governed the pattern. So to clearly illustrate the arrangement, consider the example below. We have the set of numbers 2, 4, 6, 2, 4, 6, 8, 10, 12, and so on. So if we subtract the consecutive terms of if we subtract 4 by 2, the difference is 2. If we subtract 6 by 4, still the difference is 2. 8 by 6, still we have a difference of 2. 10 minus 8, it's 2. 12 minus 10, that is still 2. So, meaning, if you will observe a certain common difference by subtracting the consecutive terms, therefore, we can conclude that this sequence right here, the set of numbers, is an arithmetic sequence. So, take note, an arithmetic sequence has what we call a common difference denoted by the lowercase letter d. I hope that's clear. I'll give an example. So suppose we have the set of numbers 5, 10, 15, 20, 25, and so on. So these numbers, or the set of numbers, this is an arithmetic sequence. So this is an arithmetic sequence because our common difference is, what do you think? So the common difference is actually 5. Because if you subtract the consecutive terms, 10 minus 5, that will give us 5. 15 minus 10, 20 minus 15, 25 minus 20, and so on. How about this one? What if we reverse the numbers? Let's say that's 25, 20, 15, 10, 5, and so on. So this time, what do you think is our common difference? Is it still 5? The answer is actually negative 5. Because if you subtract 20 by 25, that's negative 5. 15 by 20, 15 minus 20, that's negative 5. 10 minus 15, that's negative 5. 5 minus 10, that is negative 5. So in conclusion, we can say that if our arithmetic sequence is increasing, just like the set of numbers, the common difference is positive. Okay? But if our arithmetic sequence is decreasing, increasing, by the way, is lowest to highest, or from a low number to a higher number. Decreasing is from a high number, from highest to lowest high number, going to a low number. If the sequence, arithmetic sequence, is decreasing, our common difference is a negative number. Take note of that, okay? Going back, so notice in the given example above, the common difference between two consecutive terms in the sequence is 2. So the common difference is the clue that must be figured out in a pattern in order to recognize it as an arithmetic sequence. Next, we have what we call as a geometric or geometric sequence. If in the arithmetic sequence, we need to check for the common difference, so that was earlier. In geometric sequence, we need to look for the common ratio. So again, common ratio. That's denoted by the lowercase letter r. The illustrated in the example above, or as illustrated in the example above, geometric sequence is not as obvious as the arithmetic sequence. All possibilities must be explored until some patterns of uniformity can intelligently be struck. At first, it may seem it may seem patternless, but by digging a little bit deeper, that we can finally delve the constancy. So that is, for example, we have the set of numbers 2, 8, 32, 128. So try to observe these set of numbers and try to analyze from the first term, from 2, how did we arrive, or how did we get, how did we get 8? From 8, how did we get 32? From 32, how did we get 128? So for this sequence, we can say that the common ratio is 4. Now, what will we do with 4 in order to get the next term? So we simply multiply the first term by the common ratio. So that's 2 times 4. That will give us 8. Multiplying again with the common ratio, that's 8 times 4. That will give us 32. And again, multiplying by 4, that will give us 128, and so on. So, in geometric sequence, what we're going to do with the common ratio is to multiply the first term in order to get the next term. The difference between geometric and arithmetic is that in arithmetic, you will add in order to get the next term, but in geometric sequence, you will be multiplying. Let me give you examples. So let's have set A. For example, we have the set of numbers 1, 3, 9, 27, and so on. So first, try to identify whether what type of sequence is given. Is it arithmetic? Is it geometric? As you can see here, we know that this is not an arithmetic sequence because let's say if we subtract the first two terms, the difference is 2, right? For the second and the third term, if you subtract, the difference is 6. And if you subtract the third and the fourth term, the difference is 18. So therefore, there is no common difference in these set of numbers. So if this is not an arithmetic sequence, so probably this is a geometric sequence. So let's try to test. So what do you think? What's the number that we can multiply the first term in order to get the next term? So what do you think is our common ratio? So actually, the answer here is 3. Why? Because if we multiply the first term by 3, we will get the second term, which is 3. Multiplying the second term by our common ratio 3, we will get the next term, which is 9. And further multiplying, we will get the fourth term, which is 27, and so on. So therefore, this is a geometric sequence, and the common ratio here is 3. Next, let me give you another set of numbers. Suppose we have 40, 20, 10, 5, and so on. So again, first thing that you have to do is identify whether the sequence is arithmetic or geometric. So for this example, this is a geometric sequence. Now, what do you think is the common ratio? So earlier, I have a tip, by the way, I have a technique. For you to get the common ratio, in arithmetic sequence, you can subtract the first two terms in order to get the common difference. For geometric ratio, you can divide the succeeding terms. So 3 divided by 1, that's 3. 9 divided by 3, that's 3. 27 divided by 9, that's 3. So here, we can also divide. So we can divide 20 divided by 40. If we simplify that one, we will get 1/2, or in decimal form, that is 0.5. So here, in this geometric sequence, the common ratio is 1/2. It still holds true for the next terms because 10 divided by 20, that is still 1/2. 5 divided by 10, that's still 1/2. So as a conclusion, if our geometric sequence is increasing, our common ratio is a whole number, okay? Whereas if our geometric sequence is decreasing, our common ratio is a fraction or a rational number. So that's it for geometric sequence. Now let's proceed with harmonic sequence. In this sequence, the reciprocal of the terms behaved in a manner like arithmetic sequence. So take note, it is like an arithmetic sequence, the one that I have talked about earlier, but it is the reciprocal. So if we say reciprocal, we will simply get the opposite or inverse of a certain number. So if you have 2, we have an invisible 1 as its denominator. If you will get the reciprocal, that is 1/2. If we have 3/5, the reciprocal of that is 5/3. So that's how you get the reciprocal of a certain number or a certain term. Now consider the example below and notice an interesting pattern in the series. With this pattern, the reciprocal appears like arithmetic sequence. So only in recognizing the appearance that we can finally decode the sequencing that govern the series. So if we take a look at the denominators, that's 2, 4, 6, 8, and 10, we know that that is an arithmetic sequence. It just so happened that these are reciprocals of those numbers, 2, 4, 6, 8, 10, and so on. So, yeah. If we say harmonic, it's simply the reciprocal of arithmetic sequence. Next, we have what we call as the Fibonacci sequence. This was the sequence I was talking about in my previous video or in my previous discussion. This specific sequence was named after an Italian mathematician, Leonardo Pisano Bigoglio, or he is more known by the name Fibonacci. So he discovered the sequence while he was studying rabbits. The Fibonacci sequence is a series of numbers governed by some unusual arithmetic rule. The sequence is organized in a way a number can be obtained by adding two previous numbers. So this is the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, and so on. So adding the first two numbers, 1 and 1, that will give us 2. Adding 1 and 2, that will give us 3. Adding 2 and 3, that will give us 5. Adding 3 and 5, that's 8. 5 plus 8, that's 13. 13 plus 8, that's 21. And so on. So that's how the Fibonacci sequence is. Simply add the first two numbers in order to obtain or get the next number. So notice that the number 2 is actually the sum of 1 and 1. Also, the fifth term, which is the number 5 here, is based on addition of the two previous terms, 2 and 3. That is the kind of pattern being generated by the Fibonacci sequence. It is infinite in expanse. It's infinite. And it was once purely maintained claim as a mathematical and mental exercise, but later on, it was observed that the ownership of this pattern was also being claimed by some special flowers, petals, pineapple, pine cone, cabbages, and some shells. So again, we have here the Fibonacci numbers or the Fibonacci sequence. And to explore a little bit more about this sequence, the location of the term was conventionally tagged as fib of n. So this means that fib 1 is 1 because that's the first term. Fib 2, wait. Fib 2 is 1 because that's the second term. Fib 3, that's 2, third term. Fib 4, the fourth term is 3. So in this method, the fib of n or fib n is actually referring to the nth term of the sequence. It is also possible to make some sort of addition in this sequence. For example, fib 2, Fibonacci 2, the second term, which is 1, plus fib 6, that's 1, 2, 3, 4, 5, 6, which is 8. So 1 plus 8, that will give us 9. So fib 2 refers to the second term in the sequence, which is 1. Fib 6 is the sixth term, which is 8. And so our answer is simply 9. Actually, we have a formula for computing that term or the nth term in the Fibonacci sequence. It is x sub n is equal to p raised to n minus the quantity of 1 minus phi raised to n over the square root of 5. So this symbol right here, that symbol, that is the Greek alphabet phi. So that's read as phi. So here, x sub n, this one, that stands for the Fibonacci number we're looking for as to what certain term. N stands for the position of the number in the Fibonacci sequence. So for example, if we're looking for, let's say, the 10th term, so that's x sub n equals phi raised to 10. So whatever number or the position of the number we're looking for, that is our n. Phi, the symbol, this symbol, the Greek alphabet, stands for the value of the golden ratio, which is 1.618. So that's constant. That's the value of phi, or the golden ratio. Let us try, for example, what is the fifth Fibonacci number. So using the formula, that's x sub 5 is equal to phi 1.618 to the power of 5, because we're looking for the fifth term. Using the formula, minus quantity of 1 minus phi, again 1.618 to the power of 5, because we're looking for the fifth term, divided by the square root of 5. So you can use your calculators in computing. So therefore, x sub 5, or the fifth term in the Fibonacci sequence, is 5. So the amazing grandeur of Fibonacci sequence was also discovered in the structure of the golden rectangle. The golden rectangle is made up of squares whose sizes, surprisingly, is also behaving similar to the Fibonacci sequence. So take a look at the figure below. So here we have one square, and adding those two squares together, we get 2, a square with an area of 2. Then adding 1 and 2, that gives us 3. Adding 3 and 2, that gives us 5. Adding 3 and 5, that gives us 8, and so on. So the golden rectangle illustrates the golden ratio. As we can see in the figure, there is no complexity in forming a spiral with the use of the golden rectangle. So from here, we can actually draw a spiral. So as we can see again, there's no complexity in forming a spiral with the use of the golden rectangle, starting from one of the sides of the first Fibonacci square, going to the edges of each of the next squares. This golden rectangle shows that the Fibonacci sequence is not only about sequence of numbers of some sort, but it is also a geometric sequence observing a rectangle ratio. So the spiral generated by the ratio is generously scattered around from infinite to infinitesimal. So I know it's very small, but inside those little squares, those are 1 and 1, then 2, then 3, 5, 8, 13, 21, 34, 55, and so on. So this illustration right here, it's actually just like a shell. So yeah, that's it for our discussion on the types of sequences: arithmetic, geometric, harmonic, and Fibonacci. If you have questions, feel free to comment your questions in the comment section below, or you can also send it in our group chat. Thank you so much, you guys, for listening and for your time. You take care always. Bye-bye for now.